Hey everybody, Dr. A here, and in this video we're going to be providing some background information on the vector formulation of moments, referencing the Hibbler statics textbook. But before we go into that, don't forget to hit like and subscribe and be on the lookout for other material like this. All right, let's get started. In this video, we are going to be discussing the vector formulation of moments. Now, as before, we're looking at taking the moment about point O. So again, for moment about a point O, the vector formulation is going to be m vector about point O equals r cross f. Okay, now this operation is the cross product. Okay, this is a cross product, and all of these values are vectors. Vector r cross vector f equals a vector m. Okay, so all values are Cartesian vectors. So what's great about the vector formulation, whether it's 2D or 3D, if you're using the cross product vector formulation, you do not explicitly need a perpendicular distance, okay? And here's why. Let's say that we have a vector f right here, all right? And let's say that point O is somewhere over here, point O, okay? So and now let's say that here is vector r. All right. So if we want the moment generated about point O due to the force F applied at some distance r, if we have the Cartesian vector f and the Cartesian vector r, we perform the cross product r cross f, and we'll get the vector for the moment about point O. All right. Now, here's why I say we don't explicitly need a perpendicular distance. Check this out. If I project the tail of vector f back, I can plop a perpendicular distance right here, okay? And that perpendicular distance is going to be little d, and I'm going to call this angle right here theta, all right? So what do we see here now that I've drawn this? We see a right triangle has formed, okay? So what can we then say? We can say that the magnitude of vector r, all right, can be written as the following. It can be equaled to d over sine theta, okay? And the reason why we can say that is because, again, sine theta is equal to opposite over hypotenuse, all right? So when we perform this operation with vector, Cartesian vector r, the essence of the perpendicular distance, if you will, is built into that. All right, so we could write this in scalar form as the magnitude of the moment about point O is equal to magnitude r times magnitude f times sine of theta, okay? And again, as I just wrote here, the r and sine theta together, right, together make up d, right? And d is that perpendicular distance. And you see how this sine theta, if we cross multiplied it up here, we would get d equals r sine theta. All right, so that's the beauty of the vector formulation. You can apply the vector formulation directly with Cartesian vectors r and f, and you don't have to worry about trying to obtain the perpendicular distance. And this works in 2D, and it's really useful in 3D, okay? So again, back on cross product operations, remember that order matters, okay? So I'm going to make a note here. Order matters for cross product. Okay, it is specifically R cross F. It is not F cross R. If you compute F cross R, that will not be the correct vector representation for the moment about O. In fact, it'll be the negative of what you want. So you need to compute specifically R cross F. Order matters, okay? So we're going to put that in parentheses, R cross F. Okay, order matters. Now, there's another property called transmissibility, all right? So we're going to say the property of I always spell this wrong, ability, there we go, describes this behavior. So in the textbook, you need to read the subsection on transmissibility. That's a good definition that could show up on the FE exam or on one of your later quizzes, okay? The next thing we need to do is establish what if you have multiple vectors. Well, no problem there, okay? For multiple vectors, we would have a resultant moment about point O equals the summation of R cross F sub I as I goes from 1 to n for n number of cross products. Okay, so if you got two vectors each at a different R value, you say R1 cross F1 plus R2 cross F2, so on and so forth. Okay, so again, for multiple vectors or multiple force vectors, you want to compute this operation and add up all the Cartesian vector components properly. Okay, so so that's the background of this. We're going to get into a couple of numerical examples that illustrate this property. I also forgot to mention earlier in this video, R is always the position vector from point O to any point on the line of action of F. Okay, so you always have to measure R from point O to any point on the line of action of F. I implied that earlier, but I didn't explicitly say it. So we implied it with this figure. Notice we drew point vector R from point O to the line of action of the force here. Okay, so that's important, and again, we'll see this play out in our numerical examples.